to the DDN AI and HPC Data Summit at ISC 25. My name is Jason Brown, Senior Director of Product and Solutions Marketing here at DDN. And we have a great show for you today. So first, to show you the agenda, we have many folks talking, from some of our executives to some of our technical folks. We have speakers from NVIDIA and Google Cloud as well. And we're going to do a fun little panel at the end as well. So get your thinking caps on. Make sure you listen, because if you have questions about what you heard, you can ask as well. But we'll do a panel with some of our DDN experts at the end as well. And if you don't have any questions, I have a bunch of seed questions as well. But hopefully you do. So with that, welcome to Beyond Artificial.
Welcome. You have officially stepped into the future with DDN, a future where data intelligence transcends the ordinary.
We are in a whole nother era that's going to change the data center, the edge.
We are the data intelligence platform that propels the growth of AI.
We would have never imagined that the whole world would be looking for this solution.
This isn't just the next step forward. It's a leap into a world where innovation is unleashed at the speed of imagination.
That's what happens when two engineer CEOs get together.
Today, you stand on the threshold of a new era, one where challenges become opportunities.
NASA is one of the companies that trusts you.
So we're behind NVIDIA's large systems, we're behind XAI's large systems, we're behind large number of superpods.
One where data becomes a force for good.
This is going to be leveraging Purdue's strengths in engineering, agriculture, and computer science to solve the world's problems.
And one where innovation is no longer limited by the constraints of yesterday.
In my lifetime, drug discovery has been about an 8 to 10 year process. So what we're doing now is accelerating that process to a year or less.
Welcome to Beyond Artificial.
So with that, I'll welcome up Paul Block, our co-founder and president.
Am I mic'd? Does that work? Great. Welcome to ISC 2025. It seems like the years go by. I mean, it's like it feels like I'm living in Hamburg. Each time it's like the years just go. It's quite interesting. And this year, I don't know, some of you, any of you going to ISC and GTC? So, are you guys familiar with GTC in Paris? So basically, NVIDIA had the great idea of picking both shows, right? So we have ISC and GTC, same 3 days, which makes it a little interesting for us. But we're happy to be supporting ISC clearly, as well as GTC on both HPC and AI, and both of them are converging in both shows. So the only thing is that we would need an avatar to be in both shows at the same time, but I'm sure we're going to resolve this. So I'll talk briefly about updates on DDN and what we've been doing over the past year since we last saw you. So first and foremost, how many of you saw the launch of our product Infinia back in February? Anybody? A few of you guys. So within this launch that we did, a couple hours event actually on the web that was pretty successful, we had the chance of having an interview between Alex, our CEO, and Jensen Huang, the CEO and president of NVIDIA, for about 20 minutes, half hour. And what's at the end of this 20 minutes, half hour, where they basically broached about pretty much every subject from Omniverse to AI factories, to training, inferencing, physical AI, and so forth. Basically, at the end, Jensen was kind enough to say, you know, Alex, I want to tell you something. And he said, basically, NVIDIA is powered by DDN. And without DDN, NVIDIA supercomputers would not be possible. And that's kind of a cool statement, obviously. And it means a lot to us, right? I mean, clearly NVIDIA is a juggernaut in this business, and we are right along adding value, adding incremental value when you basically use DDN alongside NVIDIA technology. So super good. Thank you, Jensen, as always. Our journey, for some of you, might not be familiar, but basically the company is 27 years young. So, you know, it takes about 20 years to be an overnight success. And I think it took us maybe 20, 25 years to be we've been a success for quite some time, but I think AI is propelling us into a whole different level, right? And this is all the work that we've been doing pretty much for the first 15 years of the company, basically focusing on HPC, focusing with our HPC customers on resolving tough situations, tough infrastructure, great price-performance ratio, delivering basically better performance, better stability, better solutions than anybody else in the market. And as a community, I think the HPC marketplace made us a very good company, trained us to be excellent for AI, both in terms of technology, but also quality of our people, right? In order to deploy AI systems nowadays, we're seeing tremendous demand for HPC knowledge, for below the stack and above the stacks knowledge. And this is all basically pointing back to HPC and then meeting, obviously, the requirements of the future. Over the past 10 years, we've been working very closely with NVIDIA. NVIDIA uses DDN everywhere, basically. They were our top customers in 21, 22, 23. And in 2024, xAI became our largest customer last year. But NVIDIA is currently a customer using, on the latest Blackwell, you have 50, 60 of our systems running all the testing on Blackwell. It was the same for H100, it was the same for A100, and it'll be the same for GB300. So what's new at DDN is the company has been pretty much independent, right? Privately held, profitable, and really running with real customers, real P&L, and so forth. And so we are cash positive. So why did we decide to actually take on a partner like Blackstone and get $300 million in January to help us grow? Well, number one was validation of who DDN is, right, as a leader in data intelligence and moving forward. Blackstone picked DDN. They're not going to basically make 10 different investments in data storage and data intelligence. We are their play in this market. So this is very significant. The second thing is the $300 million is really a smallest. They wanted to invest more. We said, no, we don't really need much more money. Actually, this is really kind of a reserve in terms of our expansion and so forth. Right now, we're doing it in a cash positive fashion, but it enables us to accelerate even further if we decide to. And so this is actually helping us quite a bit. It's helping us deploy. It's helping us in strategic connection, strategic abilities, getting connected to hypercloud, to the foundation models and so forth. So they've been really helping us also at C-level suite to get access and deliver more DDN implementations across the board and more customers. So this is actually quite interesting. So at this point, we think we supercharge well over 700,000 GPU. The largest single site is 200,000 GPU at xAI, where we do training and inference, both with Exascaler and Infinia. And aside from that, we basically have hundreds of SuperPod deployed with NVIDIA across the world. We're deployed as well with HGX, technologies from either Dell, Supermicro, HPE, Lenovo. We basically connect to all these vendors equally and enable basically faster processing, faster time to result, easier and stability across. So a lot of new customers as well. And this is just a start, right? The way we're looking at it, this is just a start. What we're seeing in the pipeline is just incredible, right? Customers, HPC is actually morphing quickly into an HPC and AI convergence. We're clearly seeing the roadmap of the data centers becoming one and the same. And also, obviously, a lot of the large HPC sites have the ability to become AI factories, to become the sovereign AI for their countries, which is a great opportunity as well for people working in those centers. So it's really kind of fun to be in this world between HPC and AI and being able to see both sides that are basically now converging probably into one side of the next 3 years. So really what we do is we accelerate and simplify HPC and AI workloads. And as you scale, this is becoming more and more important. So we clearly see as what we see as a second wave in this kind of implementation of GPU and AI and NVIDIA technologies. We're clearly getting into a mode where it's common nowadays to deploy 1,000, 4,000, 8,000, 16,000 GPU. And when you get to those scale, it's becoming more and more important to acquire the right data storage, data intelligence. Although, at first, not many people care about it, right? You pick on your GPU, you pick your network, and then at the end of that, we say, oh, by the way, I need storage. but it's actually quite important, and we're seeing a big difference on various sites that might or might not pick DDN as far as the efficiency of the systems. And we can now compare it because a lot of the centers have multiple technologies, so they're able to basically tell us exactly where we excel, where we might lack, and then we basically work towards basically filling those gaps. But in terms of performance, scalability, and so forth, I mean, we're number one. There's nothing basically getting anywhere close to DDN. Why? Because we ingest faster, we pre-process faster, we train faster, we checkpoint faster, and we do the inference. Now inferencing is coming in, right, with KV cache and so forth, and we're ready to do this with Infinia as well as Exascaler. So really, at the end of the day, what we're telling our customers is that if you look, the efficiency of the system is super important, right? You're investing a lot of dollars into GPUs and network, and you want to make sure that this system is efficient, running at 99.999%, and basically is available at all times. So we've improved also all our monitoring, management, online upgrades, all this is done, right? So Exascaler and Infinia deliver enterprise-level quality with HPC-like performance, right? So you get the best of both worlds. So checkpointing, super important, right? If you have 1,000, 5,000, 10,000, 50,000, 100,000 GPUs tend to fail. And at this point, checkpointing is super important, that you do it synchronously or asynchronously. At some point, you're going to need basically to feed the data to the data storage. Model loading, data loading, listing objects, all this is super important, right? For example, at XAI, we accelerated the listing of objects, right, before you do a simulation several times a day by 6,000 times, right? They started by telling us that basically all they needed was the performance of 10x AWS, and then when they started really running on 200,000 GPU, it was way too slow. So at that point, we basically worked with their engineers and our engineers, basically, and we basically arrived at 6,000x the time. So some of our technologies we're finding with Infinia, the advantage is also the partnership with centers, where we control all the development, and what we're finding is this technology is really enabling to workloads. We can really optimize it to get better result and faster result from your application, right? So we play now both below the stack, as well, historically, IT infrastructure, HPC infrastructure, and now we're starting to play above the stack, really lining up to models, to workloads, to inferencing, and so forth, and accelerating actually the workflow with our Infinia technologies. So clearly what we're finding where we're differentiated is, and we're seeing it actually, customers, at first, obviously, they're learning, they're doing the modeling and so forth, and at some point they're starting to understand the efficiency of the system, and we're getting there. We're not fully there, but we're getting there, and that's where basically they find DDN if they haven't found us yet. Because they are seeing basically some of the latencies or multi-writes issues or multi-back and forth with back-end network problems. What we've done is we've excelled at really having a very, very short pass to data in a parallel fashion, no matter what the scale of the system is. So you'll see in this that really this is kind of a convergence of HPC, training, inference, and both of our technologies, Exa 6 and Infinia, are perfect for both. And at some point, they're converging over the next 3 to 5 years. Some of our customers, jump trading, that has probably, that's an interesting one in HFT. They probably have close to an exabyte of our storage at this point, right, data storage. And right now, accelerating with GPUs as well. So we're seeing a lot of GPU buy and investments in the financial community. Roche, that is both sequencing and life sciences acceleration. Manufacturing semiconductor KLA. Scaleway is one of our NCP partners in Europe. We also have Nebius. We have Nscale. We have a bunch of them. And then Cineca has been a long-standing customer of ours. And we have Daniele talking from Cineca a bit later today. So what's new also is DDN is cloud-friendly, right? You will see from us that we're delivering cloud-native partnerships. The first one that has been announced is Google 1P, right? So how many of you have actually contracts with GCP? Okay. How many of you have contracts with AWS? 1, 2, okay. Azure? Couple, okay. And OCI? Okay, so you guys are mostly on-prem still, very good, okay. Are you guys planning to go cloud a little bit for bursts or something? Is that something that you're looking at? So the beauty of, for example, Google 1P, and we anticipate that over the next year we'll be in 2 or 3 of the hyperscalers, is the fact that you can instantiate the same workflow that you're doing at your site in a very quick fashion, and it can be basically temporary, or it can be at the scale that you decide. So the Google 1P was launched a month ago or 2 months ago, and we're getting into way too much demand, and so they have to reset kind of the plans because by July they need to expand it in a much bigger way. So we're finding that clearly on-prem is here to stay, but cloud is booming as well. So where we are is we're investing a lot in engineering, right? We just don't have enough engineers, right? So if you guys want to join DDN or you think that you can help us, please let us know. We need creative, we need designability, we need deployments, we need across the board. We're growing across the board. Last year, we grew about 65% compared to the year before, so it was a successful year. This year, we anticipate about a 50% growth as a minimum. So I mean, again, it's an exciting market. But we view it from a HPC going into AI mentality, right? It's about real value. It's about delivering results. It's about delivering 100% on time and obviously uptime. So a lot of exciting things. Hope ISC will be a great show for you. Welcome again, and welcome to DDN. Thank you.
Thank you, Paul. Appreciate it. Good insight. I was interested. Good questions too, by the way. I was unaware of the mostly on-prem audience here, but it's good to know. But we do have a speaker from Google talking later about Google Managed Lustre, which I think you will find interesting. So next up is one of our sponsors of the event, one of our supporters from NVIDIA, CJ.
Great. It's great to be with you here today. Delight. Feel like I've developed a lot of friendships with people that are here, getting together every couple weeks for the last 8-10 years, something like this. So we've gone through a lot together. I'd like to, just as DDN and many others are trying to develop and share some insight, I'd like to try to see if I can share some insights as we've been looking at what's the right design for a data center and what's the right design for storage architecture and storage technologies with this. So we have been collaborating in a number of different ways. One of those is in AI. Obviously, I hear DDN is an AI company. NVIDIA is doing a little bit of that in that space too. So we've been basically introducing this design that kind of brings together this new generation for enterprise storage to integrate the inference with the agentic reasoning workloads. There's a variety of different components that we're putting together in a mix, and we'll talk about some of those. There are also a number of hardware components, and we'll talk about sort of where some of those are fitting. Also touch on a little bit of some initiatives that I'm driving in the space of looking at what's missing in the hardware and what's missing in the software, particularly for a subset that we think is a growing subset of the Gen AI workloads that need a completely different objective rather than terabytes per dollar of getting IOPS per TCO. And we'll talk just a little bit about that. We'll also touch on some storage certifications. So borrowed a couple of slides here that were used in joint presentations at GTC between Sven and Nave. And so this kind of touches on what's now become more the table stakes for things that DDN has helped provide some leadership in, being able to, as data comes into the data center, of triggering being able to build new vector data indexes out of that and store the embeddings to be able to search that very quickly and where needed to be able to get things at a very low latency, for example, in object form. One of the applications for this is an AI virtual assistant. And in this case, again, you see a number of the similar things that we saw before. SQL is one of the ways that people are now going to reach and access the data that we have. And we'll spend a fair bit of time talking about a KV cache and why that's important and where we want to go with that. But all of this, this is basically building up a platform from the bottom of, instead of saying, well, just go provide the data, of being able to make it more available and integrated into the NIMs and so on that we provide for being able to generate insight. And there's not one size fits all, but you need a platform so that people can do their own work and development in that space. So one of the things that we collaborated on is in this space, if you look at the fundamental problem of embeddings, of taking too much space and being difficult to manage and access. So we worked essentially on trying to compress those so that we could efficiently hold and represent and access the embeddings. Okay, that's nice. Now, what's the next thing that you run into is, after you have those embeddings, they don't do you any good if you can't find them. You can't go and look at every one. You need an index for that. And the process of indexing that data takes a lot of time. People have traditionally been doing that in CPUs, for example, in Milvus. And so this is now being enabled by something that we've offered called QVS for vector search, that enables you to both search and generate the indexes on the GPU. And you see 6x and better speed up from that. And by building this together relative to an AWS baseline with DDN Infinita, together you're getting over 20x performance improvement in that space. So better together. DDN has been one of the first in each of the different platforms, starting with SuperPod, to be able to get a storage certification. What we really care for you as customers, joint customers of DDN and NVIDIA, is that when you get something out of a box, you know that it's going to work and you can depend on that. So that's part of what we're have this NVIDIA certified components and storage in the working together also on the storage side of NVIDIA cloud partners. So that's something that DDN has been doing a lot. So one of the key takeaways that I'd like to challenge you all in is it's very disorienting. I've never seen things move anywhere as quickly as they are now, where I said in my boss's staff meeting recently, we were talking about some things related to KV cache, and my answer to a question was, well, I think I know what it is now, but the one thing that I know is that it's going to be different in 3 weeks. That it is really changing every week as to what the implementation looks like, what the best way to do it is, what the innovations are. And so these different kinds of usage models that we have that are emerging are really important to understand. So I'm going to try today to give you some insights into those. And for each of those, I like to look at in each area for each of the different usage models of asking, what are the key metrics? What are the figures of merit that really matter and that you know when you're doing it right? Because you can speed something up, but it actually doesn't matter in the end, and we'll show some examples of that. Just as an example here, that when you have a machine talking to a machine, a multi-step agentic state, instead of, if you're a human, you're waiting for the first token to come out and you're twiddling your thumbs like, oh, finally it started answering. All right, that's a time to first token. But if you're a machine, you don't care about the first token. You're going to wait until you get the whole answer, the whole output sequence. Then you're going to go start working on it for the next step. And so those figures of merit are different in those cases. And in some of these emerging applications like GNNs and relational graphs, vector database index and search, there are cases where the sparse fine-grained IOPS are the thing that matter rather than the sort of terabytes, or the bandwidth or capacity optimized things. So one of the things that you can look at is not just for performance, but what makes it easier to build infrastructure. I'll show you in a picture a little while. We have an infrastructure that we use in inference called Dynamo that calls on Nixle. And it's less work because the natural way to go and look up something that's in your KV cache is using a key. It's easier if you don't have to go through an extra mapping table to turn that into a file, and you can naturally do that, right? So that's an example. There are cases where the things may not matter that much at your compute node, but there's a much better total cost of ownership in the back end by being able to do things more efficiently with RDMA as an example. And we like giving you choice in what it is we're doing. So in these performance areas, these are some fairly traditional different performance metrics that we have at the bottom. Okay, so I'd like to just kind of zoom way out and look at the differences that you'll see between what goes on in compute and storage. So there's some things, certain kinds of problems that you're trying to solve closer to the compute space. An example of that I'll show you is when you're trying to load a model, that if you're ask it a question and there's say a variety of different models for a mixture of experts, you want very quickly to get to the right one. Some of those are for throughput, others are for the throughput sometimes matters for the KV cache or for HPC or data analytics. When you have a large amount of data that Paul was referring to, going back to remote storage, for example, for checkpointing and other kinds of things, being able to use a network that is capable of doing congestion controlled and adaptive routing can help you out a lot there too. And in the back end is, again, you want to be as efficient as possible with RDMA to get maximize your TCO. So some of the main performance takeaways that I'm going to offer here just as a peek for this is that performance at compute, and whether it's at the compute server, the network, and the storage server that we just showed, it can differ. And understanding and tracking those as they change over time can be important. Sometimes accelerating storage matters a lot, sometimes not very much. But there are cases where it can matter a lot, and you want to bring the best tech to the table for whatever the case is. So in this inference model loading case, you essentially, each different model, it's a figure of thumb is it's about 2 gigabytes per billion parameters. So it's not too big a deal if you have 7 billion, but if you have 405 billion parameters, it just may not fit in your GPU at all. You can't have a lot of those and keep those around in your GPU. And so you need to swap between them, and when you do, bringing things in from storage, whether it's local or remote, in a hurry matters. In KV caching, how many people have heard of or are familiar with KV caching? All right, quarter, a third. Okay, so the basic idea here is that as requests come in, this is an input sequence length. There's something you basically, across multiple turns, you have lots of users that may go ask a question, go get a cup of coffee, and come back again. And so there may be lots of state that builds up, and you have to put it someplace. But you've seen this before, and each time you ask the next question in sequence, you need all the information from all the previous questions that you've asked and the previous outputs you've gotten. And so you could throw that away and recompute it every time, or you could cache it and keep it around for the next time. And maybe there's a common prefix, there's a similar prompt that you share with somebody else that you can also take advantage of. And there's a notion lately of disaggregated inference, where you separate the prefill, the part that's working on chomping through the input sequence, versus decode that's generating the output tokens. And when you want to bring things back in from the cache, you can say, well, where are the biggest pipes, or where are the most pipes? Computationally, prefill is heavier than decode, so you can have more GPUs. And so if you're using the traditional north-south connections that's sort of going out to the internet and remote storage into these GPUs, there are more pre-filled GPUs, as you can see here. Once you get them in, you're gonna, if you had computed it, you would have computed it in the pre-filled GPUs and send them over to the decode, and we can use that same east-west network to send them over there. And so we can make these trade-offs to figure out what's the best way to do this. And that east-west network tends to have more NIC connections and faster ones than you would go to the north-south, so that's not a bottleneck. So when does this matter? So you want to look at the time that you take to sort of reload versus recompute that OSL. as a function of sort of doing the decode and so on. So this is kind of the essential formula that we have here. And it's worth using this KB cache if you could load it back in faster than you could reload it. So there are a number of factors that impact this. Basically, if you have a bunch of, relative to what you did before in this state, there's a long question that is being asked now, then that's new, you've never seen it before. So if that fraction is high, then that's going to sort of wash out the time that you're taking to load back in. If you don't have very much state because what you've seen before is not much context, or you can move it really fast because you have a fast network or lots of GPU load targets, or the decode because you have a long output sequence, again, kind of makes that fraction of I/O small. And OSLs tend to be limited to about a page. Nobody wants to read more than a page of output. And so that's about 300 tokens. It could be much larger. But the ISLs tend to be growing here. So I just tried to do kind of a what-if exercise. So I tried to remove some examples here from a potential that could appear that weren't realistic. But essentially, across these different models, there are a couple different models, I took and sort of used a trend of how do I, most of the time, at least within each model, find conditions. It's kind of a Hamming distance of a couple of things that I'm, parameters that I'm increasing, like the amount of state or how long it is, or making the network slower, or dividing it across fewer GPUs. But still, in this case, the total amount of time to which I'm going to apply acceleration tends to be in single digits. And so we get very excited about how much of a difference this can make inside the node, but it's often not that large. But it can be very appreciable out at the server side. And so that's a very important place to be able to do that optimization for the KB cache. And to keep all this state across all these different queries, you'll need a lot of this. And likewise, checkpoint save and restore. I thought that this was going to be a really big deal for storage acceleration. And as I look more closely at it, if it's a small system, you can see sort of it goes up with to the power of the GPUs for your failure rate. So in a small system, it can be a couple days before you have a failure if you're only at 10 GPUs. But if you're at 1 million GPUs, it may be only like 18 seconds or so. But in 1 million GPUs, you're going to take your state and spread it across so many GPUs that total time that it takes to move it is rather small in that case. So a completely different kind of application are the graph neural networks, where you're capturing the relationships. So language models are good at making associative relationships, but if you want to, in a pairwise fashion, but if you want to look at the grander scheme of being able to look at groups of things and how they relate to each other, GNNs are very good in this way. And they're very applicable to things like fraud and social networks and so on. And essentially, the key thing that you're doing here is when you go and you take, I've got this big graph, I'm going to find the smaller one that I care about to go train on. You're using every one of 100,000 different threads, each trying to access its own data to figure out, based on the embedding data, which next node am I going to go visit. And so you have 100,000 threads, each trying to access data that's too big to fit in memory. And so that's where you want to do something with storage. And that's very fine-grained because the size that they tend to access in that case is more like 512 bytes, which is very different than bringing in a very large image that you used, is it a cat or is it a dog? So this can induce numbers like in Gen 6 of getting 100 million IOPS per GPU, which is pretty radically different. So we talked before about how we've seen significant benefits from QVS of being able to generate the vector databases on a GPU. So the different technologies that we're working with, GPU direct storage, I'm the co-architect for that. We've had QFile, and DDN was one of our first partners that implemented that. And QObject is something that is seamlessly integrated under an S3 client so that you can do an S3 over RDMA. The Spectrum X is something that has been used to improve the throughput and jitter at the cluster level of using adaptive routing and congestion control, and also scaling up of the SuperNIC. And then this new programming model of scaled accelerated data access, SCADA, is something that enables the GPU, all of those GPU threads, to be able to get to unbounded storage so that you can work on problems that you were too big to be able to work with before. The speed there of your solution scales with the number of drives you have and how fast IAPs are. So we've looked at the performance gains that you get from the congestion control from Spectrum X that can be on the order of 1.4 and more for each of read and write on a large-scale NVIDIA system. And DDN has a blog on this. So just to kind of wrap this up as a call for action, I hope that you come away from this thinking, wow, there are a bunch of different usage models. Some of them, the performance storage acceleration really mattered, some not so much. Some at the compute side, some more at the server side, and understanding sort of what are the key objectives there, and distinguishing sort of what the requirements and acceleration are for each of those. And then tuning a storage architecture to meet those needs, and sort of leveraging the best available technology that we have as we've been doing before, and sort of watch for those new usage models may drive new SKUs, which is an effort we call Storage Next. Thank you very much.
Thank you, CJ. Appreciate it. And thank you to NVIDIA as well for supporting the event. Really appreciate that as well. So next up is a DDNer. You may have seen him before. You may know him. Mr. James Coomer, our SVP of Product, who's going to talk to you a little bit about what's new at DDN, what we've been doing for the past year or so since last ISC.
You know, it's interesting what CJ was talking about from our perspective, because, I mean, I guess that's why you're all here. Storage really isn't storage anymore. It is an active part of the workflow. It's right in there. As we call it, from our perspective, above the stack. It's no longer somewhere where you put your bits and bytes and then hopefully get them back later in the same order. It's actively a piece of the pipeline. It's become what we call an intelligent data platform as opposed to storage. So it's genuinely, the technology is changing, and what used to be storage is now elevating itself into the stack to simplify, cost reduce, and accelerate various different pieces of the end-to-end AI workflow, which is a great introduction to my talk. By the way, thanks to CJ. Did you just leave? We've been working with him there you are, a lot. What a great team. And our team here, some of who are hiding in the audience as well. Noel, is he here? We've been engaging very closely with them on all these areas that CJ, as far as I know, is kind of fronting from NVIDIA's perspective. Lots of very cool technology about how storage can make the whole end-to-end AI better, faster, more cost-effective, etc. So I'm going to talk about what's new in HPC and AI. But first, I thought I'd ask you a question, just because it's fun and you get to do something. Are you an HPC person or an AI person? I know that's a stupid question, but I'm going to ask it anyway. I'm going to ask you to put your hands up if you're going to say you're an HPC person, or put your hands up if you're going to say an AI person. So HPC first. Old school, hardcore. Okay, AI people. Crazy new people. Yeah, that's very good. Right, HPC audience, there we go. And one guy. Very good. Well, we've got something for everybody right here. Firstly, DDN's probably known for these appliances, right? The 400x2, 400x3 supercomputer scale systems that tend to be delivered in hardware, right? Everybody's nodding yes. But it's not really true anymore. We'll hear about it later, so I won't talk about it a lot, but great news from Google, partnering with DDN to use our exascaler, our developed software, to support their platform. We'll hear more about that later, but it's very cool, and it means that we now can deliver our extreme efficiency and performance through a public cloud with all the supportability and hardcore engineers behind it to give you support. So that's thing one, a big move into public cloud and neo clouds, but we'll talk about that again. Second is much stronger technology to enable us to partner with the server vendors. Today we have solid agreements with Lenovo and Supermicro. We've actually deployed close to an exabyte on Supermicro already. So we have the technology to run on these pure server platforms. Really nothing, I mean, I won't denigrate their systems, but nothing particularly special in terms of the core technology is required. We need a cool CPU, we need some flash, we need memory, we need a network, and then we're good to go. We can form a resilient data platform and go from there. So that's new, and that didn't happen last year, and it's happening at massive scale right now. And we also provide our own platforms as we did before. But more than previously, we'll see an exception in the next slide or two, but we create these server platforms for our software technology. And of course, we're just really competing with others. And you might choose a Supermicro or Lenovo or a Dell or an HPE, or you can choose a DDN, and we don't mind. It's our software which is bringing it together and forming a cluster. And we'll offer you our hardware, and that might be a better option, it might not be. So different world right now. Not only do we have these appliances, but we also deliver in cloud, NCPs, NVIDIA cloud partners, third-party servers, and also with our appliances. At any scale. I can feel my 10 minutes slipping away pretty rapidly with my 17 slides. We saw this slide before, but just a little bit of clarification. Who in this audience knows the difference between Exascaler and Infinia? Let me ask that question slightly better. Who knows the difference? Let's just put it that way. Right. I know it's hard, isn't it? We throw all these product names at you, and it's so difficult to really absorb them and see what they mean. But underneath, I'm product manager, so I'm VP of products. So we do have two primary products for HPC and AI. The one you're probably most familiar with is Exascaler. And we've been shipping that for 20 years. We have the team that develops the open source Lustre code, which we build upon. It's at our core, but we build upon that to deliver as Exascaler, hardened, easier to manage, simpler, etc. That's Exascaler. And its primary purpose in life is to deliver efficiency to massive scale CPU and GPU systems, so that if you spend your 100,000, 100 billion on infrastructure, then by using DDN, we're going to give you more productivity out of it because you're going to be waiting less time for your data. Quite a simple proposition, right? But at massive scale with great robustness. Now, Infinia comes along, a different animal completely, totally different software. We've been developing it for 7 years. And it's designed to tackle all the complexity challenges around AI, but also HPC research data. In fact, of course, they're all kind of tackling the same kind of problems. We've got more metadata is distributed, we're trying to track it, we're trying to govern it. Research data management, AI, if you're on the HPC camp or the AI camp, it's all good news for you. And that's what Infinia is for. So think of it as a new version, a new era for a new kind of AI native data lake. So it's designed to be very scalable, very fast, allow you to share, be very resilient, allow you to move data around the world, and basically cover off the complexity of managing large-scale, complex workflows from end to end. So, summary, before we go into the next 15 slides in the next 2 minutes. Exascaler is primarily there for efficiency and scale. It's a file system. It runs in parallel. We've been using it in supercomputing world for 10 years plus. And Infinia is entirely new software designed to tackle the end-to-end complexity challenges of this AI world. So I'm going to give you a couple of peeks into what we've been doing in the past year and what we're about to do across these two products. We're going to start with Exascaler. Well, in fact, we're going to start with both. Look at this complex diagram here. We keep showing these complex pictures, but don't worry about the details, especially at the back. But what we got here is a mixture between an HPC world and an AI world. So the whole audience is now entirely happy. Right here, we've got CFD. We've got something like Fluent running here, OpenFOAM. And we're running traditional HPC workloads. And our Exascaler platform is ideal for that. We cope with parallel I/O. Very, very well optimized for this parallel I/O. We're going to run these parallel applications extremely well. with CFD, or pick any other application. I think I saw some people interested in materials modeling who should not be named in the audience earlier on, but any HPC application. But this new world is bringing this part of the picture. A foundational model trained on the general area of HPC, this case it's aerodynamics, must be trained by the HPC model to become specialized in a certain use case. And the result of that is this surrogate model. And the surrogate model is going to do your specific type of CFD in this case, faster, better, lower cost, simpler than the old school HPC way. That's the idea. So that's what's happening in the next 5-10 years. We take something like Fluent, we use it to train a foundational model to get a surrogate model, a surrogate for Fluent, which is going to do its work faster, cheaper, quicker. But that requires a different sort of infrastructure. Not only do we need the old school, let's say, super fast file system, but we also need the new school to handle the models, to support the Kubernetes environments, to support the inference, to support the models, the KV caches, the embeddings, all the stuff that CJ was talking about. We need that stuff as well. So that's really why we have this what we call the intelligence platform, incorporating both of these. One's to support this new complexity of the new world, and the other's to provide this massive efficiency, performance, and scale that's needed to support the sheer scale of training and of HPC workloads. For Exascaler, this is a new platform. So this is news, the AI 400X3. Zooming out of the screen towards you is now the fastest DDN platform on the planet. It's going to do 140 gigabytes a second. That means you need fewer of them to support your GPU infrastructure, and you need less power, you need less space, you have less to manage, and you basically support more GPUs for training, more CPUs for HPC with less. So that was launched a while back, available today in various flavors. Come and talk to us and we'll tell you exactly about the flavors there. Minus 28 seconds. So I'm just going to tell you a couple more things in the last minus 4 minutes about a couple of very cool features from the past 6 months. So firstly, cloud. So everybody seems to be doing cloud. It's even in the HPC world, we have organizations who want to be able to deal with multiple tenants and segregate that data, right? So we often find the world of finance is particularly concerned about this, separating out this department from this department. And we've done a lot of work, now coming up on 3 years, to make sure our Exascaler platform is doing the right thing when it comes to enabling yourselves to build a multi-tenanted platform. And I'm going to give you 4 slides in quick succession, and at the end of those 4 slides, you will be convinced that we have the best approach to multi-tenancy. Firstly, we've made it easy. All of these policy layer items allow you to use a set of APIs to build your multi-tenanted file system. Whether you've got 1 tenant or 1,000 tenants, we can use a single set of API calls or command line calls to create a multi-tenanted environment. That multi-tenanted environment will allow different tenants, different groups, to get secure, isolated access to their data, and that isolation might include L2 networking or L3 networking. Doesn't matter, we're very flexible in the networking layer, so we can support a wide range of security paradigms with, well, as I said, our single management domain. And I'm going to use my last minus 2 minutes to show you a little demo of that. I got 5 minutes, that's great. So look at this first. What we're showing here is, if you read the manual, how you could go and create some tenants on an Exascaler file system. But do you want to read the manual? Nobody wants to read the manual, do they? So let's have a look at this little demo here. So what's happening here is we've joined up the 2 worlds. We're running an Exascaler file system. We've downloaded a model. We've pointed a model at the manual so it knows what to do. And then we're just asking the model questions at the bottom here. What are OSTs on this file system? In normal, natural language. And the model is consuming the manual. It's then interrogating a real live file system and providing real English results here. So it's kind of 2-in-1 demo here. We're showing you the future of managing complex infrastructure. Just type in what you want. It'll do all the hard work for you. You don't have to read the manual. It'll do that for you, and it'll give you the result here. And the other thing we're doing is showing you how easy it is to create tenants. Look, we just created 2 tenants, Coke and Pepsi. Obviously, they don't want to talk to each other. So we're making them separate and segregated. And now we're going to create 2 pools, just using English. We could use German as well, I expect in the future sometime with a future update. We're using English just to create some pools of storage and allocate them to the 2 tenants so that they're properly segregated. And there we go. We've just done it, and the pending state is just there while we form those pools. And then we're going to check the list of OSTs, storage targets in those pools. And it's going to consult the manual, check the API, run the API against the real cluster, and give us a result and say which of the tenants have which of the OSTs and all that kind of stuff. And then we're going to delete everything and start again. So pretty cool demo. We are developing this technology, so natural language processing interface into your environments. And of course, it doesn't matter which environments you've got. You might have Infinia, Exascaler. You just talk English or German at the thing and ask it to fulfill your function. So working on that, and we're already done the contents. All these API calls already exist in Exascaler 6.3.3, available today from DDN. And then that will be the end of my presentation.
I know that you had many more slides. You can go for another 5 minutes if you wanted to.
It's too much for them to take.
It'll blow their minds too much? All right, that's fair. All right, perfect. So thank you, James. James will be here for questions. We're going to play another short video, and then we're going to have about a 10-minute break in the foyer. You can get some refreshments, cool down a little bit. It's a little warm in here. Apologies for that. We had the AC cranking earlier, but I can only do so much. We are in Germany. Having AC is a luxury anyway, right? That's what I've been told. I'm from the USA. So we'll play a quick video, and then we'll have about a 10-minute break.
Here at Blackstone, we've been investing in digital and AI infrastructure for over a decade. We invested in our first data center from Microsoft in 2015, and we provided a very large financing for CoreWeave just as ChatGPT was being launched. And as a result, we saw the explosive growth of AI and HPC computing solutions. Today, we're looking to invest in AI from end to end, from the infrastructure layer all the way to the software stack. One of the things that got us so excited about DDN is Blackstone is seeing the opportunities that AI can create for business today. If you add up all of Blackstone's portfolio companies, we would be a Fortune 10 business. And across all of those companies, there's a significant opportunity to increase efficiency and provide value at scale through AI. But to do that, you need to find a way to ingest and utilize large data sets, exactly what DDN does so well. Companies like xAI, NVIDIA, and many others that we are seeing are embracing this technology for their critical workloads. DDN is at an important inflection point today as it launches its latest software product, Infinia. Infinia is disruptive in 2 important ways. First, within the stack, at the data center layer, Infinia enables much more efficient compute by reducing the costs of running extremely expensive infrastructure. And second, above the stack, at the application layer, Infinia enables a significant speed up in the ingestion of data, leading to a 10x performance boost to developers, increasing the ROI for product companies. We used to talk about how software is eating the world, and today, the one thing we know as a trend that is almost without fail is that AI is going to be eating the world. And when we think about companies like DDN, especially with the Infinia launch, we think this investment in this company is poised for an extremely bright future, and we couldn't be more excited to be partners with DDN.
All right, folks, we're going to get started again for the second half of our data summit. I want to make sure that you'll get to our reception sooner rather than later, so I don't want to delay anymore. So in this second half of the show, we're going to have 3 speakers. We're going to have Wyatt from Google Cloud to talk about Google Cloud Managed Cluster, which is powered by DDN Exascaler. We're going to have 2 DDNers. We're going to have Andreas, who's going to talk about the future of Exascaler, which was our parallel file system that James was talking about before. Then we're going to have JT come up as well, and he's going to talk to you about a very interesting topic that I think you'll find, at least I found it interesting, so hopefully you will too. After that, we may or may not have a panel, depending on timing. We'll see. And then we will have the networking reception after that. So without further ado, I'll introduce Wyatt Gorman from Google Cloud.
Awesome. Thanks, everyone, for coming back from lunch outside, or our reception outside. My name is Wyatt Gorman. I'm a product manager for high-performance computing at Google Cloud. I've been with Google for about 7.5 years. And before that, I was at companies selling Lustre as well as GPFS and some other cloud storage, and I was a senior systems engineer. And if anybody can tell me what company I was at afterwards, I've got a prize for you. So come find me later. So I want to talk a little bit about our new managed service for Lustre. It's our latest and greatest storage offering. Tell you a little bit about why we built it, why we partnered with DDN, and about HPC on Google Cloud in general. I was actually really interested to see that show of hands that Paul did earlier. I can appreciate that none of you are GCP users, Google Cloud users, because I know that almost all of you are probably Google users, so no worries. It just means you're all potential customers, and this is probably the best presentation I'll have at ISC because I've presented to maybe 60 potential customers, and my boss will be very happy. So thank you all for being potential customers. So at Google, when we think about high-performance computing, which we've been doing for several years, I'll show you a roadmap slide in the next slide, we think about our platform and what we offer in 4 key pillars, or in 4 key topic areas. So that's fast and affordable, easy and compatible, partner preferred, and then best of Google. So fast and affordable on the far left really is talking about our infrastructure and the underlying bits of our platform that make the compute, network, and storage great and work well for HPC workloads, of course, but especially AI workloads. I'll admit we definitely have more spend on AI than HPC within Google Cloud, but it's pretty comparable, and we're not far behind on the HPC side. We used to be, obviously, much more heavily focused on HPC, but lately you can't avoid it, and obviously Google has a lot of pedigree on the AI side. So we've been working with a lot of folks on the GPUs and our TPUs and so on, but core HPC components like our new H4D CPU platform with AMD based on their 5th generation EPYC platform is absolutely essential, and building those kinds of key infrastructure components like our managed Lustre service is really important and the very foundation of what we do. Easy and compatible is about our platform, the actual upper layer of that stack, so how you deploy that infrastructure, right? The ways that you have to consume it, and intelligent things that I'm not actually going to have time to get into, but things like our new dynamic workload scheduler, where instead of querying the cloud for VMs one at a time or in batches, you can make your entire request to Google Cloud, 1,000 nodes or 10,000 nodes, and Google Cloud can not only schedule that for you, meaning that if you don't need that immediately, if you wanted it in 2 days or 2 weeks or a month, we can delay that for you and schedule that for you with a discount for giving us that ability to bin pack on our own. So we're doing a lot of interesting things within the platform to make running HPC and AI-type workloads or large-scale batch workloads work really, really well. As well as building new things that, again, I won't have time to talk about, like Cluster Director, which is our managed cluster service, which will integrate with managed Lustre and give you a unified, fully managed platform to run your HPC workloads with Slurm, with Symphony we're working on right now, LSF, whatever the job scheduler is, whatever your storage is, and so on, although obviously we have a suggestion on storage. Partner preferred comes in more on the earlier side of our relationship with DDN and the sort of story that's led up to this, which I'll tell in a couple slides. But it's about working with our partners and making sure that when a customer goes to a partner, as much as they can, they would recommend Google Cloud to those customers because we're the first to a managed Lustre service with DDN, or we were the first to B200s with NVIDIA this year, right? So just giving them those reasons besides, oh, we like them, to suggest Google Cloud as their HPC or AI platform. And then finally, bringing the best of Google to our customers. So these are things like our global network, especially for financial customers or even large-scale customers doing design around the world and wanting to move their licenses with the sun or something like that, right? Exchanging large amounts of data with large scientific projects like the LSST project, if anybody's familiar with the LSST telescope, getting terabytes of data off of a mountain in Chile up into the US to process it every day, right? That's where these kinds of worldwide network or our capabilities in Kubernetes really come into play. So apologies for the formatting. It's converted from Google Slides. In 2017, we really came into the HPC sphere. And a lot of our history with DDN came about in about 2018, 2019. This is a more recent slide where you can see we've made significant investments in some things that we've been working on for a very long time, like our integration with Slurm, with the SCED-MD folks, but also newer things like supporting HPC on GKE in a really meaningful way. Or last year, bringing FPGAs onto the platform with Atos and working with Illumina, as well as now introducing RDMA onto the platform. So it's taken us maybe a few years to catch up, and we're not shy about the fact that we were early on serverless with App Engine, but nobody wanted it yet. And we were late to the game with GPUs when everybody wanted it. But now we are definitely hitting the sweet spot and bringing together all of the bits and pieces that folks might want in a full and complete HPC and AI environment, especially at the extreme scale. So that's where you see managed Lustre coming in. And all of this comes together into a complete HPC platform that I'd love to tell you about a little more later. But today we're talking about the storage component of the bottom layer and then the partner software in the open software layer, right? So we had a problem that came about. And we've had a lot of history with this problem that I'll talk about. But the problem was that HPC mostly, and AI in some cases, applications need large-scale concurrent reads and write access to large-scale storage, right? Is anybody unfamiliar with this problem in this room? No hands. Aha, okay. So this isn't unique to HPC, right? This happens in AI, although a lot of that is more coincidental or sort of pleasingly parallel, so to speak. Thousands of nodes loading the same PyTorch libraries all at the same time, right? Bogs down an NFS server a lot, right? So some of these AI customers are just using Lustre because it's fast and it's parallel and it happens to fit well. But it fits really well. And a lot of our HPC users need HPC as well. I say that this isn't new to us because we saw this problem back in 2018, even earlier than that. We started building open source Lustre solutions. We started contributing to like the Lemur data mover project and things like that back in the day. But in around 2018, we started partnering with DDN. And it was obvious that they were the ones to work with to build these kind of Lustre solutions. And so we brought them into our marketplace, first with open source Lustre with WAM Cloud. And we set some IO 500 benchmarks, actually. At that time, we were the #2 Lustre system in about 2019, excuse me. And then we brought Exascaler to the marketplace, and we set the #1 Lustre benchmark that stood on the IO 500 list for a long time. So we have history building these large-scale Lustre systems, very performant Lustre systems in cloud for people who obviously need them, right? And over the years since then, we've seen the shortcomings and the demand for a fully managed Lustre system and the shortcomings of the marketplace kind of offerings that we had. So we partnered with our friends at DDN, who we've worked with for a long time and who obviously have that history and knowledge about Lustre, and we brought managed Lustre to the ecosystem. Now I'll admit, as we go through these, this was just released, this is early days, and all of us are Lustre experts or have been around Lustre for a long time, and this is gonna be missing a few things that you might expect. But this is private preview, right? We're in early days, and we're mostly focused on building the capacity and the performance first that people need before working on the higher level solutions and policy engines and all of these sorts of things. So our managed Lustre service in its infancy is built as a persistent storage offering that contrasts to some of our other storage offerings that I need not mention, but it has full Terraform support. It's supported in GKE with a custom CSI driver right out of the gate. So no need to bring your own or fiddle with anything, and it's very shortly going to be a fully managed CSI driver, so you won't even need to do the install or anything. You just trigger it when you launch GKE. It's fully integrated with our storage transfer API, which I'll come back to, and obviously it's a POSIX file system. The specifications that we have are pretty straightforward. We have up to 1 terabyte per second of read throughput currently, and I'll share how that scales in a second, but we scale up to petabytes, millions of IOPS, and compared to some of our other storage offerings, and this might be a bit of a wrong thing to say about Lustre, it excels at random I/O. And that's has a lot to do with the SSD backing that we built this system on now. You can expect significant performance optimization, especially for your AI workloads. We get very high VM throughput, up to about 20 gigabytes per second to a VM on our large-scale GPU machines, and obviously support thousands of VMs in a single namespace, thousands of clients in a single namespace. Where we see a lot of performance improvement, especially in AI, besides the coincidental parallel I/O, is in checkpointing and in writing out checkpoints, especially because our local SSDs on our GPU nodes are not yet exactly how large we would like them to be. So a lot of people benefit from that, although next generations are going to be larger than we need. Currently, this is available in a large variety of regions. This is actually a really widespread initial launch for a managed service within Google Cloud. We always deploy within every sort of geographic region, and at least one region, but this list is at least twice as long as a normal private preview, so that really shows you how many customers we have demanding this and all the places that they're demanding it. And a lot of these coincide with where our large-scale GPU or TPU deployments happen to be. So in terms of performance, we have 4 key performance levels. I'll actually skip to this slide and I'll come back. And they scale linearly with your capacity, right? So this is a set of options right now. We have 125 megabits per second per terabyte, or terabyte, excuse me, all the way up to a gigabyte per second per terabyte, right? So that scales out to then, a terabyte per second per petabyte. And these are the current performance tiers, I'll say. There are customers already pushing us on either end of this sort of scale, and so you can certainly expect to see this shifting. The price correspondingly scales, so the performance at the lower tier is actually probably cheaper than a lot of our other storage offerings. So it's a very performant but very cost-effective option for our customers. And then in terms of what's coming in general availability, you can expect all of the sort of standard baseline support that you would expect: directory quotas, full VPC service controls, that managed CSI driver for GKE I mentioned, but also expanding that capacity. So we're going up to 8 petabytes with the GA offering, and you can expect that to continue to scale both up and down. Right now it's 18 terabytes minimum, up to a petabyte, but we're going to go up and down on either end. And then you can also expect to see in the future dynamic caching with GCS, automatic data tiering and backup, and then compression, deduplication, and all of those types of things to help make sure that this is cost efficient. And a lot of that is thanks to capabilities that we already have in Google Cloud Storage, as well as encryption with CMEK. This is just a little more data if anybody's interested in some more of the sort of read-write IOPS and latencies that we get, and the kind of throughputs that we see in IOPS. And then finally, how do you get access to this, or how do you move your data to managed Lustre and get access to it from GCS when you want to move data back and forth or to another storage system? Our storage transfer API is actually built for this. It was built before we had a managed Lustre service, but it's a storage agnostic, containerized, agent-based data mover. And so basically you install a container on your source storage, a container at your destination storage, and you call a Google Cloud API that coordinates that data movement and does all sorts of multi-part upload, download, splitting, multi-threading, and all sorts of optimizations that are already inherent in our GCS data movement, our Google Cloud Storage data movement for object storage for large-scale data movement. So you can use this to go directly to cloud storage or to an on-prem Lustre or an on-prem GPFS or whatever. It doesn't care as long as it's POSIX on either end or object storage. I say this doesn't have right now a policy engine or anything like that. So that's the kind of thing where we have the plumbing there, and we're working on making sure that that plumbing works really, really well. And that this works fine for a lot of AI customers who know exactly what data they're moving and need to access at any given time. But we recognize that HPC users might be a little bit less capable of specifying every file that they might need to access. So that's where stubbing and policy engines and all of those sorts of things come in. And with that, I added a link there, but if you want to sign up for the private preview or get access to it, let me know. It's a really capable system. I've been playing around with it recently, doing some simple benchmarks, but obviously it's DDN exascalar, so it's rock solid and it's really performant. And we have that history of optimizing that we brought to this solution from the IO 500 experience with my co-conspirator or collaborator, Dean Hildebrand, if anybody knows Dean. And then we have plenty of documentation and information available online for you to check out. So please go ahead and read about that. Find me here or join us at our reception on Thursday evening, and we'll have plenty of folks that you can pick our brains about Managed Lustre. So with that, I'll hand it back.
Thank you, I appreciate it. I know it's always great to see collaboration with technology partners, especially someone like Google Cloud, who, as we know, HPC is typically on-prem from our poll, but it's going to have to expand to the cloud, especially with the economics and the way things seem to be going. All right, up next we have Andreas from DDN. He's going to talk about the future of Exascaler, which is our parallel file system primarily used for HPC and model training.
Hi, thank you. So today I'm talking about Exascaler, and as you know, it's really deployed across the spectrum in terms of large GPU clusters, large CPU clusters in the HPC world, and it's seeing a continual growth in terms of features and flexibility in deployments in various environments. And so I was just trying to highlight some of the areas that we're working on. The current Exascaler 6 is actually doing really well in terms of features and functionality. We are working on Exascaler 7, and there's actually quite a few new features that we're working on to deploy in there. And the target date is not totally set yet, but it's scheduled for early, like first quarter next year. And so there's the features that are in there that we're starting to develop: file level data resilience, and that's come about because we want to have both a resilience that's above the level of the hardware, but also because of cloud deployments that we want to be able to deploy on hardware agnostic storage. And while we are optimized very closely with the SFA storage, there's quite a number of sites that want to deploy on cloud native. And of course for Google, right, we use the resilience at the block storage layer, but that doesn't provide us any advantages over the avoiding timeouts because of our server failover and things like that can interrupt application workloads that, while they don't fail, they may wait for minutes waiting for the servers to fail over. And so we've been asked to develop resilience at the file system level. And so this is being done through data mirroring, what we call immediate data mirroring, and erasure coding. As well, we're working on metadata resilience at the block layer so that you can mirror across different servers and get redundancy across racks and in case of storage device failure. As well, the management server is also being shifted over to what's called Raft, and I'll explain this later so that we get availability above the hardware level. And then a nice feature for end users, is we call it trash can undelete. And that lets you have essentially a virtual trash directory, like a Macintosh, so that you can see files that were recently deleted. And then this will be accessible to regular users so that they can recover their files in case of problems. So the immediate data mirroring is what you would expect. The clients can write directly to multiple copies of the file. And so while we've had what we call delayed mirroring for some time, that would give you mirroring on the order of a few minutes after a file is finished writing. And we've been using that functionality in our Hot Pools product, which we use for tiering between flash and disk, so that you'd write the data into the flash pool, and then a few minutes later it gets mirrored into the disk pool, and then when you need the flash back, an hour or a day or whatever later, and the flash is running out of capacity, we can release the flash mirror. But this is changing the paradigm so that the data is written immediately at the time of write from the client. And so the nice thing about doing this replication at the file system level as opposed to at the block level is that the clients can immediately read the traffic or read the data from multiple copies on the servers, right? So you get, while the write performance may be reduced by half, it depends on whether the storage and the network is actually saturated or not. It happens asynchronously in the background. Well, not in the background per se, but the writes are sent in parallel, and because they're buffered writes, then it's not slowing down your application. But then on the read side, you can read the multiple copies, and it improves workloads, especially single-threaded data workloads like model loading and things like that. You actually have double the bandwidth on the read side. And so this gives us the other nice thing about the immediate data mirroring. One of your servers goes offline, instead of having to wait for the server to restart, or if there's any problems with the recovery, you can read from the second copy within a few seconds, right? And so this really helps the availability for training. Similarly, we're working on file system level erasure coding, and as you'd expect, this is we can configure it to be 8+2 or 16+3, having redundancy across servers. And one of the nice things about this erasure coding implementation is that it will be upgradable from existing systems, so that you can actually add erasure coding to striped files after an upgrade, right? So you can take your existing data and add erasure coding to it. And the initial deployment will be the asynchronous erasure coding. So we would anticipate doing writes into the file system in a mirrored mode. And then once the files are cold and you don't need the bandwidth from the mirroring, you can do erasure coding in the background and reclaim your space, but while maintaining resilience across server failure. Fault-tolerant MGS. This is a feature we've been working on for a month or two, and it's quite nice. It allows the management server to be always online, and it will actually be running on multiple servers concurrently. So it's not a failover model anymore. There's actually multiple live servers, and they'll handle mounting and recovery tasks from any of the servers concurrently. And so again, this is giving us availability above, what the hardware is providing, and also gives us a building block for moving more of the metadata services to be redundant, right? This gives us the foundation for improving the MDT service to be redundant as well. And so this will be the initial phase, it's just the metadata management server, But things like quota management and internal databases on the MDTs will actually be replicated across multiple servers. And this one, trash can undelete, is what you would expect from your desktop, right? You delete a file. Oops, I didn't mean to delete that file. An extra star in that RM command. And so the structure of Lustre itself underneath is actually very amenable to handling this, and we have to add in the virtualized namespace support so that we already had a two-stage delete where you delete the name and then separately you delete the objects. And now we're deleting the name and putting it into a virtual holding directory and then making these trash directories visible on the client so that users can recover them, in cases of problems or potentially malicious deletion. We've had some cases where, runaway scripts are accidentally deleting, parts of the file system, so you can recover from that. And the users can do it themselves, which is nice. And then after some time, there'll be a policy to delete the old files, or if you get close to filling up the space, right, it will be properly integrated with the namespace. And the other area that's been discussed already a bit today is the tenant isolation, so multi-tenancy, and we're doing quite a bit of things here. I won't get into all of the details, but really, we spent 20 years making Lustre and Exascaler to be aggregating a number of servers into one big file system, and now we're slicing and dicing that file system into small slices again. But the nice thing is that we've provided isolation in terms of security, authentication, capacity, and performance between the tenants. All of the ID spaces are mapped separately, and so the tenants don't necessarily see that there's other tenants there. And there's strong crypto level authentication of the clients to be able to to coexist in the same file system. As well, we have data encryption for extra security, right? I mean, there should never be a case when tenants can access each other's data, but we can do data encryption. And so this actually protects the data from even the storage administrators, because only the users are managing the keys. And so even the data at rest is encrypted here. Client-side data compression, this is actually a feature in Exa 6, but I thought it's worthwhile to mention. We're getting nice compression here. We've had a number of sites using this already, and they're getting data compression ratios between 2 and 4 times, depends on the data. In some cases as high as 6 times compression. And the nice thing is that this is totally transparent to applications. And so especially if you have large data sets that are text-based, or of course depends on the data type, but we won't compress. We automatically detect if the data are already compressed. What else? Hot pools, I think we've talked about that. I'm going to go through these a bit quicker. Hot nodes, that's client-side data caching, again, transparent to the application, so that if you're doing training workloads where you read the same data multiple times, it's can cache the data in the local storage of the client nodes. It's saves the servers. The other big area that we're working on quite a bit is the management framework, and so this really simplifies the management of the servers. So instead of doing running lots of manual commands to do upgrades and installs, EMF is orchestrating this in the background, and this is what actually powers the Google managed Lustre service in the background. So it provides an API for deploying and managing servers, and this is actually very useful in the cloud environment where you want to be having repeatable and interface driven deployment. And together with EMF, it manages, if you have on-prem hardware, it really simplifies the integration of upgrading the firmware and the whole software stack in simple steps and orchestrates them all. We've done 100 server upgrades, running a couple of commands. So this is actually makes the operation very much repeatable. Other things in the software stack that are improving, Prometheus exporters, so that we can export statistics from the servers and integrate with on-prem Grafana. Nice DDN insight if you have that. It's providing nice charts. We've been building an infrastructure called LIPE Scan and LIPE Find, and it can generate nice reports. And then Insight is consuming the storage reports, gives you histograms, a directory level consumption, and various reports. And because it doesn't do namespace scan, it scans directly on the storage. It runs very efficiently. And that's it. I guess I will be available for questions in the panel. So, thank you.
Thank you, Andreas. Appreciate it. Some good information there, especially if you're an exascaler customer. I mean, I'm fairly new to DDN. I've been in DDN about a year, almost, in July, and so I've learned a lot about the technology and the products. And from what I've learned of previous versions of exascaler, some of these improvements are game changers. So hopefully, they were as exciting to you as they were to me when I learned about them. All right, next up is JT. JT's going to talk about AI factories.
Okay, so today I would like to talk briefly about the difference between AI and scientific AI. So part of this talk, actually, some results are coming from a European research project that we are coordinating. So some of it is still a work in progress, I would say so. So we have already seen this slide. So we have two very well-educated and distinguished speakers, CEO of NVIDIA, CEO of DDN, talking about the future of AI. So what will be the future of AI? Maybe we will have multiple futures, and maybe we will have a diverse implementation of AI depending on the field. And specifically here at ISC, where there is still, I will say, a lot of HPC interest. So to back up this claim, actually, I look at the compression ratio of various data. So Andreas shows us, this very nice feature where we can compress automatically the data. And as you can see on the rightmost column, depending on the data, you have a different compression ratio. So I would say that data is a code for AI, right? So it seems to me that the same AI model, which is very good for text, may not be that good for floating point or FP64 data that we love in HPC. So probably this will have implication also at the architecture level. One point about this complexity, and I think we are a bit underrated for this, so we are still a very strong open source player, and it's a differentiator in the sense that we understand the complexity and we have, I will say, a deep insight about the requirement of our customer. Basically, we are writing codes with you guys since years and years, right? So, of course, fortunately, DDN is not the only open source provider for Lustre, but we are taking the main part of it, and it gives us insight about what CF, for instance, which is also collaborating to Lustre, is really needing in terms of Lustre implementation. And this open source commitment is not going to disappear, so it's even maybe becoming, I will say, more important for the company. So for the moment, we are working with the Lustre community in order to push back the Lustre client within the Linux kernel. We took over also maintenance some part of Linux. For example, libfuse now is maintained by DDN. So okay, let's see what is a very nice supercomputer for AI. So this is a superpod. So you have this massive amount of GPU for doing all the computation. And from a data standpoint, this is served by this little rack of DDN hardware, full flash, very high performance, very dense, very nice. However, when we are talking on the field with our customer, I mean, HPC people, they love flash. Flash is nice. You can throw whatever I/O pattern to it, it will cope with it. However, they still love hard drive, because hard drive in terms of capacity, price capacity, it's a very good value. So we are already differing a bit from a traditional AI customer, if I can say so, in the sense that we want hard drive. And we are still in love with tape. So we want flash, hard drive, and tape. So we are already quite different from an NCP customer here. And I think this is one of the specificities of the scientific AI market. So still talking about the specificities, so we have this nice plot about, the need for checkpoints. So we all know that in AI, checkpointing is not only for a fault tolerance purpose, right? It's not because we are afraid of, breaking the hardware. It's because also it's the nature of the computation itself. We have this overfitting slope where at some point we need to stop the training because the accuracy is decreasing. And we need to overtrain quite a bit because actually the decrease in accuracy is not this nice red slope, but this is a blue one with a lot of local minima. So you need to overtrain quite a bit to be sure that you are out of a local minimum and that you have really overtrained, and then you have to roll back to the last relevant checkpoint, the best one. Okay, so we need to checkpoint. There are some implications to this, is that in the reality of the workload, we are not really specifically in HPC using the full machine in order to do AI training, because people tend to have small model for each of their very, I will say, scientific domain of interest. So for instance, in your European project, we took already trained model and we fine-tune it on 8 GPU. So it's not 1,000 GPU, it's 8 GPU, but we want to have a very good bandwidth out of this 8 GPU. And this is something that Andreas and his team have implemented. This is this notion of hybrid I/O, where basically the Lustre client is now smart enough in order to choose, depending on the size of the I/O of the payload, if you need to aggregate this to coalesce all this small chunk of data in a cache and then throw it over the network, or if the payload is large enough in order to go and to be efficient directly on the network. For checkpoint, we are manipulating large payload. This is a single line of PyTorch save, and you have your whole model out. So on my 8 GPU, thanks to this hybrid I/O, I'm enjoying a 10x performance improvement. So it's not augmenting the performance of the storage file system itself, it's more about efficiency from a limited number of clients. And this is what I want when I'm running multiple models on my system. So this one, I did this last week, and I was wondering what is the impact of power on I/O pattern. So power also, this is something which is very important for HPC player because we have a lot of power constraints in our site. We are not NCP where we can use like hundreds of megawatts. Power is very important for us. So running different I/O pattern and looking about the power consumption, I fill up this table, and there is a couple of, I will say, takeaway from this. So the first one is that you can saturate your box. So I have here, it was a small box, so 50 gigabytes of peak performance. Using read, I can saturate my bandwidth, and I'm using 510 watt. For write, if I saturate the write bandwidth, I need more watt. So write is more power greedy than read. Okay, one thing. The second thing is that playing with the I/O pattern. So here I'm running full speed with very nice I/O payload, like 4 megabytes sequential write. So this is a perfect I/O world. This one, this is the opposite, the nightmare of the I/O world, random 4K, all over the place, single file. So what I do observe is that I have a strong decrease in bandwidth, like by a factor of 30, but also I'm saving like 25% of watt. So the question is that what is the best I/O pattern in order to do my checkpoint? So I can summarize this by 2 histograms. So this one is basically time-based, and the other one is power-based. So if I have to checkpoint every hour using this box, so I tweak a bit the I/O pattern in order to limit the bandwidth to 10 gigabytes. So I can simulate, I will say, a slow storage, and my fast storage is my 40 gigabyte box. So if I'm running with my 40 gigabyte box, my fast storage, I will have over 1 hour in order to checkpoint my model, I will have 1.5% of time overhead. If I'm using the slow storage, I will have like 4.5. Okay, so this is a time thing. But now if I'm looking only about the power, so what is best is that actually even if writing fast is costing you more power, actually it's so fast that you are saving a lot of power. So using a fast storage, you will end up with probably something like 4.5 kilowatt in order to checkpoint your model. If you go for the slow storage, independently of if it's synchronous, asynchronous, or whatsoever, you will have to spend 3 times the amount of power. So as we are used to in HPC, faster is better, right? So even if it's a bit counterintuitive, it's much better to write fast instead of writing slowly. So again, it's not a question of synchronicity. Okay, so a lot about training on checkpoint, but we know also that in AI, our pipeline are much more complicated, right? So we have all this data pre-processing and we have post-processing. And the question is that, do we have, this one size fits all? So here, in order to try to characterize this a bit more, I will say, in a more granular way, I went for this roofline model, which is quite used in the numerical simulation world, where basically people used to try to assess if a numerical kernel was more limited by the floating point capabilities of the platform or of its memory bandwidth. And then you end up with this kind of simple graph where basically you try to put the dot where my numerical kernel is. Should I go for a faster CPU or should I go for a faster memory? So recently, there have been some work in order to extend this roofline methodology to AI pipeline. So again, this is the AI pipeline that I'm using in my European project. So it's 5 stages, and we are taking as an input satellite images, and we produce automated metadata generation. So here we use a paper which has been published last year as supercomputing. So it's coming from Berkeley Labs. And their idea is to try to apply this simple roofline model in order to know where is the bottleneck in my pipeline for every stage of the pipeline. So we try to, we start the work. So for the moment, it's still a work in progress, right? So we only characterize one stage of the pipeline, but it's already something. So using the exascalar probe, it's easy to grab the I/O pattern. So I can quite easily, put a price tag on this in terms of power. So I have the I/O pattern, and now I can look at the various hardware bottleneck in my system and check where is my workflow stage. So here, in my example, I have the blue line, dash line, is about the limitation is a HBM bandwidth. And then the green one is a GPU, CPU memory bandwidth. Then after the red one is the I/O bandwidth, and here, I'm here, right? So when we did the work for the workflow, we are not limited by any of this factor. Actually, the limiting factor is a parallelism. So we are not able to extract enough parallelism in order to saturate the box. So it would mean that basically we could run the same workflow on a smaller GPU with less parallelism. We will get a similar performance in terms of throughput. So as we have different, we are doing this work of characterization because we know that we have different data platform, right? So we have the exascalar, we have Infinia. And the idea is to try to find which stage is the most suitable for which platform or the other way around. So Infinia has already been introduced quite a bit. So it's very good for versatile and diverse I/O workload. You can do whatever you want with this. However, for extreme performance, exascalar is still the most suitable tool. So this has been also presented by James Coomer previously. So the idea is that for what we foresee as being a modern HPC data center, we'll need a mixture of these two data platforms, one for the training of the model, and then when we'll use this AI inference stage in order to check what is the quality of the input, we will run this on Infinia, and depending on the result of the inference, we may decide to go for a full simulation, like a bit accurate simulation that we will run again, exascalar again. And once the result has been completely produced, then we expose it to the customer through Infinia. So architecture-wise, we end up with something like this. We still need this massive amount of GPU, so there is no question about it. We need GPU, right? But we will need also this exascaler system for the training and for the HPC workload, because on this GPU, we will run a lot of traditional HPC simulation as well. However, all this data versatility, this data pre-processing, post-processing, the consumption, the cloud-oriented consumption model, everything else will be run on Infinia. So this is what we foresee for a scientific AI factory these days. And I guess that's my 2 cents.
Thank you, JT. Appreciate it. All right. So, another poll of the audience. We've been going for about 2 hours. Do you want to have the panel, or do you want to go have drinks? Who wants to have drinks? Raise your hand. Okay. Who wants to have the panel? Raise your hand. All right. Well, we know which one wins. So, if you want to talk to one of our experts, Mr. Coomer, Mr. Dilger, or Mr. Acquaviva, as well as Mr. Gorman, you can do it while you're having drinks and food in the next room where you came in. Before we go, though, I have to do a few things. So first off, I wanted to play one last customer video. We haven't had a customer video played yet, and usually we'll have a customer present, but we want to have a very technical speakers instead, so we did that. But I want to hear from Cineca, who is an Italian company. Daniele was here. Is he still here? Daniele, are you here? I think he left. But anyway, I'll play this. Then I'm going to tell you a little bit more about what we're doing at ISC, the DDN, and then you'll be free to have some drinks.
I am Daniele Cesarini. I'm a project manager and HPC technology specialist at Cineca. The main mission of Cineca is to support Italian and European research through our computing infrastructure. The outcome of our project improve the human research, ranging from weather prediction to astrophysics, nuclear fusion, artificial intelligence. We started collaboration with DDN almost 10 years ago. DDN today supports all our large-scale systems. DDN intelligent platform allows us to compute 30% more data that we usually do in our system through the capability to ingest and process such amount of data. DDN technology is pivotal in our AI project because Cineca today is in the transition phase between HPC and AI. In the future, our mandate is to support both ecosystems, so having a data platform that is able to support both workloads in our large-scale system is strategic for us. So DDN technology enables us to do that.
Yeah, Cineca is a very interesting use case. They do weather forecasting, tsunami prediction, but also some of the more traditional HPC and AI workloads as well. Like I said, if you want to ask any DDN experts or anyone else, we can do that afterwards. So, for the rest of the show, just wanted to inform you of some of the activities that DDN will be participating in. So first and foremost, thank you to all of you who came today. Thank you to all of our speakers. Thank you to NVIDIA for supporting us. And we hope that you've at least found something interesting about today. Hopefully many things, but I'll take one as a win. If you're interested in talking to more DDN folks or engaging with us, we do have a booth. It's booth E01. I believe it's right by the entrance. And the booth floor is now open. It opened at 3 p.m. Or 15 if you're following that time. So we're open, and you can go there. There is the opening gala tonight at 6:30 or 18:30, where I believe there will be networking and drinks on the show floor as well. So if you want to interact with us more there, we'll have some demos, we'll have some experts there as well to talk to. Please join us. And then all day tomorrow we'll be there, but also probably more important about tomorrow is the DDN After Dark Party, DDN After Dark Party. So if you want to join us for even more drinks and talking to even more DDN folks tomorrow night, feel free to join us. I believe on your tables is the QR code to scan if you want to join us and register. So please feel free. It's from 7 to 12 a.m. At the Gaga Club, which is on the, Reeperbahn. Hopefully I said that right. And it's about a 10-minute Uber or a 30-minute walk if you're feeling adventurous. As well, we have some presenters and some workshops. So Santosh went today already at the Google Community Workshop. But tomorrow we'll have Andreas and Peter talking at 10:15 a.m. And then JT will be going on Friday as well. So if you want to, like I said, learn more, we have opportunities. So with that, thank you, everyone. Appreciate it. Please enjoy the rest of your time here at ISC, and please enjoy the networking reception. Thank you.